Hello and welcome to Lars's Electric Endeavors. In this video we are going to be controlling this little DC servo motor with our Nucleo board. And this is a small motor device where we have 3 wires coming to it. There is a power supply, 5 volts, there's ground, and then there's this control signal. And the control signal uses something called pulse width modulation. And you can see an explanation here. It basically means that you send pulses, and the width of the pulse instructs the motor what position to put the shaft at. And the wider the pulse, the more clockwise it will put the shaft. So we will be configuring a timer and a PWM output of our STM32 micro to generate a suitable signal today. And we will be using Cursor's AI to our benefit here. And we will make it work as good as possible by making a rule and adding a skill to it. If you stay tuned in this video, you will see how exactly we will do this. But first up, let's continue where we left in the last video. So in the last video, we just got everything working with Cursor. We got the connection working to the board, and we made a simple test case for the button. But we didn't do something which is, I think, very mandatory, and that is to have the IntelliSense working. Right now, the IDE doesn't understand that this is C code. It's not really helping me. We need to install a plugin here that will give Cursor the ability to parse the C code. This is the plugin we're going to use. And I just want to show you the installation here because it may be a little bit tricky to get it right. The most important thing is that you allow it to install the clangd language server. There it is. It's very important that you allow this. And it's probably best to wait with the restart until the clangd is finished installed. There you go. We can go back to our files. And then we need to understand that the clangd plugin uses this file for the configuration. This file came from the STM32 Freedom Kit. And it's going to be looking in the debug build folder. And we don't have it right now, so we need to make a debug build. So there we invoked the build script, and now we have we just made a debug build, and we have all the files in here. And I believe the language system is looking at all these commands to understand exactly what are the include paths, what are the compile time defines, and so on for when we are building the software, so the IntelliSense can really follow how is the software being built. And you can see already now that things are looking better. We have an underline here. It's able to find the include, and if I push F12, it can bring us to the file. And if I hover over a function, we now get a proper description here. And if I, yes, immediately I will get suggestions based on the symbols visible in the code right now. So that works. But I'm going to do a bit of configuration of Cursor as well here, because I just pushed Control, comma. That brings you to the settings. I really don't like the theme here. So I'm going into the appearance here, and I'm going to choose Visual Studio Dark. I like that better. And also, you see these small hints here. This is not text. This is something they call inlay, and I can't stand it. So we're going to turn that off. There, it disappeared. And there are other things that we're going to change when we start to use Cursor here. The next thing that we didn't do last time that is really important is to set up the Git, the source control here, so we can commit the state of our source. And I'm simply going to write git init here in the root of the folder. And then we can look here. And let me just mention that when we took the files from the STM32 Freedom Kit, we did get a git ignore file with some sensible defaults, I think. So at this point, we have basically our source here. And interestingly, you see that all the STM32 CubeMx code is going to be committed to source, but it's only the code after the processing of our script. If you remember, the Freedom Kit has a script where it takes the code generated by CubeMx here, makes small changes to it and puts it in here. And we are not going to commit the code here, but we will commit the code down here. So all in all, I'm just going to add everything here. Yeah, very creative commit message. Maybe we should save. Yeah, and this is a fresh install of Linux, so I haven't set my username and my user email in Git. And let's just do that. Follow the guide here. Username. And user email. Okay, let's see if it works better. There we go. So now we are looking better here in Cursor. But before we start to actually do the stuff we need to do to control the server here, let me just show you the rule and the skill in Cursor I came up with to make things work better. So basically, the rule is I don't want the AI agent to modify the files in the CubeMx folder. Because I was playing around with it and it was making changes in here. And that's a very bad idea because every time we generate code in CubeMx, this folder will be totally changed and those changes here will be erased. We should only make the changes in our source folder here. So that's the basic purpose of the rule. And here you can see we need to make a folder called .cursor/rules. And let's just do that. And here I will add a rule called where to edit MDC. And I'm just going to copy paste it here. What files to edit and not to edit. Basically, I want it to stay in the source folder, and I will instruct it that we have something called a hardware abstraction layer in here, and we have an interactive test suite in here. And importantly, you should never edit files here. Okay. And the other thing I want to give it is I want to make a proper instruction to Cursor how to run the build script, because the build script can do different things and it may be not too intuitive without an explanation. You can use the build script to build the test suite, or you can build the main application, or you can also program this device with the result of that. And I feel like the best way to do that is to make a skill. So we will do that. Cursor. Oh, and by the way, here you see something called compact folders where The cursor folder has no other sub-member than rules, so it's displayed on one line here, and also that's something I don't like very much. It's called compact folders. There we go. And now we are messing with settings here. You see the indent? I just think it's tiny. I like to set it a little bit higher. There we go. So, cursor, skills, I believe. Cursor skills, and then the name of the skill, and then a skill.md file. I want to call it, let's see here. Oops. New folder. Build and program. Oh, shut up. Not now, please. Unbelievable. Okay, I managed to make it shut up about the restart. Okay, here, build and program, and then skill.md. And here I'm going to paste this text. Build the application or test suite and program target if desired. The main purpose is to check for compile errors after editing code. So this is basically the AI should use the script basically to make a compilation and see if it worked out. And here are the usage instructions. And let's just see if we named that correctly. Yeah, I think that looks right. That looks okay. So, okay, armed with that, it's time to start the real task of today. And the first thing we want to do now is we want to configure one of the I/O pins on this chip to generate the PWM. And I actually tried to ask the AI to do this for us by going in and modifying the CubeMx file. It did not work. So at least at this point in time, it's still something you have to deal with yourself, and you still need to have some knowledge about hardware and about the architecture of this chip to make this configuration. You may ask, why aren't we just using Arduino development environment here? Of course we could do that. We could easily control a server using that, but then there is no learning curve. There is nothing to be learned here. The purpose of these videos is to learn how to actually program this chip directly without any cheating. And we will be writing code that's native for this platform. We will be using professional tools and then also AI as an assistance. So let's open the project. And now comes the question. 1 second. Yeah, so now comes the question, what I/O to use. And if you look at the board here, there is a small label next to these different in-outs. And these labels, they do tell us some information, but actually they don't tell us the whole truth. We have to look at this pin out here of our board. You can see A0 is PA0, but A5 is something totally different. So my point here is just that you have to find a pin out to be sure what you're dealing with here. But I investigated and I decided to pick the one called A0. So this particular pin right here is PA0 in our chip. And this is the one we find here. And now I'm going to choose something called timer 2 channel 1 for this pin. So that means STM32 CubeMx is going to configure this output to be controlled by the timer 2 channel 1. And where do we have that? Here we have the timer 2. And now is the time to configure this timer. So you have to know that these timers, they are extremely advanced. They can do so many things. And we are just scratching the surface here. And also that's why it's useful to use this tool here to generate the boilerplate code to get started easily. Otherwise, you would literally have to spend a couple of days to understand the datasheet and how to configure this timer. So let me just show you what has to be done. We have to pick a clock source. And since we are using the channel 2, not this one, sorry, the channel 1 on timer 2, always double check. I need to enable channel 1 here as a PWM generation output. We are in timer 2. And how does it work? So basically the timer has a 32-bit counter, and it will keep counting until it reaches the period, and then it will start back from 0. How fast is it counting? Now we have to look a bit in the clock configuration here. This might be intimidating, but we don't really need to understand all the steps here. What's important now is that you can see the timer clocks here. They are in our current configuration being fed by 84 megahertz. So that's what we need to know. This timer is incrementing with 84 megahertz. And what we will do now, we will not start with the servo. We will start with an LED. Look at my little construction here. Because we want to make a sanity check that we actually are generating the pulses like we want them to. So what we will do now, we will make the LED blink once per second based on this PWM output. And if I type 84 million here, that means with an 84 megahertz clock cycle going into the timer, it will reach the period once per second and restart. So like this, we will have a timer with a 1 second period. And I want it to auto reload. I want it to make a PWM. And this is the pulse width. So basically, what percentage of the time do we want to make a high level, and how much time will be a low level on the PWM output? And here I will just put 20,000, 20 million. So that means about a third of the time we will have a high pulse coming out of that pin. And that should be all we need to do in here. So I will just save and generate. So now, as you remember in the Freedom Kit, after generating the code, we need to run this script. And now we have updated the source in here based on the new generated code in CubeMx. And now that we have source control, we can take a quick look and see what changed. So we got a bunch of new files. We got some new functions. We have a timer init function now. We have all the configuration based on what I picked in the UI. So very nice. Let's see if it builds. Yes, of course it builds. So what we want to do now, so we are not done actually. If I started at this point, let's just try. The way I wired this is that the resistor end, this is a 470 ohm resistor on a red LED. This end has to go to positive, and the other end goes to negative, the way I wired it. So there, that should be correct. If we just try and run it now here, nothing is going to work, do any difference. Also need to insert this. we need to call a function called start timer, start PWM, and we need to make some function in our code tree in HAL to control this. And we're going to use AI for that. So now the task for AI is, please add functions to the HAL module for controlling the timer 2 PWM output. There should be a start function, stop function, and a function to set the duty as a percentage. Also add a test case for these functions. The user should have the option to use keys to start, stop, and pick certain duty values. Let's say 1 for 10%, for 25%, and 3 for 50%. Key. Yeah. Do it, please. So now the hope is that the rule and the skills that we gave the AI here should lead it on the right track to actually solve this task correctly in the first go. It's doing a lot of stuff. Learn, build, and program. It looked at our skill and it was able to run the build and see that we didn't get any errors. So it made a start and a stop and a set duty cycle. Perfect. And it made a program here in the test case. Let's just take a look here. I'll just keep all. PWM start, PWM stop, set duty percent. Yes, exactly. You have to call the start and the stop. And here it's looking at the, yeah, it's retrieving the full period value, and then it's calculating the percentage based on that and putting it into the compare value. That sounds correct to me. And it added a test case. Start PWM, stop PWM, set duty cycle. Okay, that looks totally right. So we built the test and let's program it. And now we need the terminal emulator program here, PuTTY, as you saw in the previous video. Let's just reset here. Help button. Okay. Start PWM. There you go. It's blinking. Duty cycle 50%. So now this should be equally amount of time should be on off and on the LED, and it looks right to me actually. Let's try 10%. Yeah, it looks correct. Good job, AI. Let's just verify that we have 1 second here, because it's always good to verify. And if we take a look at this watch here, I'm looking at the second arrow. And it seems to me we have perfect alignment with the seconds and the timing of this pulse here. So that indicates everything is actually working as we wanted. I think that's a good time for a commit here. I'll just add everything. Duty P generation 1 Hertz for test works. Okay, so we have a way to generate a PWM signal, and it's doing what we want it to do. So now the next step is to make the right signal for the servo. And basically, we need to pick another period. So this period, as I explained before, will give us 1 second interval. I'm going to use a little calculator program called Speed Crunch here. But if we need 50 Hertz, then we should use this value as our period. And I suppose that's it. We will run the script after we generate code in CubeMx. And we see now there is a difference. Yes, exactly. This is the correct way to change these files, because we want everything in the CubeMx folder to be controlled by CubeMx. We should never make changes here by ourselves. So I suppose we're ready to run. If we start the output now. Yes, now we get like a solid color. Actually, yeah. So when I look at the LED, I see it like slightly flickery, less than full intensity light. But because of the aliasing of the frame rate of this camera, you can see it flickering. But I would say it is in fact flickering with 50 Hertz as we want it to. There is one more thing we need to adjust here. If you remember here, in order to make signals suitable for the servo, we should not make very long pulse widths. We should only make short pulses like this. So 1000 microseconds, that's 1 millisecond. So that's like 5%, and this is like 10%. So let's change the test case a little bit here. Here, let's get our agent. Change the PWM test case. Let's make it a little bit different. To start with 5% duty cycle, let's use plus and minus keys to have 5% and 10% duty cycle available as 1 and 2 keys. Other than that, plus and minus should increment or decrement the duty by 1%. I'm sure you can figure that out. Exactly my point. I'm sure it's correct. So we start and we pick 5%. Yeah, that looks all right. Plus increments, minus decrements. Now I feel it's time to connect the servo. So let's start with ground. Ground goes into ground here. 5 volts go in here. Let me just see. And then we will put the control signal at A0. Okay. And now 5%, 10%, plus, minus. It's beautiful. And now we have a way to test the extremities of the servo. How much can we go in each direction here? Let's just try. Okay. Oh no! Really? That that really? I don't think you're supposed to do that. So you should stay within the limits of correct pulse width. 10, and if we go higher, it just gives up. Okay, sure. So 11 seems to be a proper upper limit. And 3 is the other limit. So 3 to 11. Okay. We have successfully brought up this servo now and can control it now based on these functions here written by AI. I think that's pretty neat. Let's just finish this. Make a HAL function named servo control that takes a boolean for a percentage from 0 to 100 that should convert to 3% to 3% to 14%. That is set as the PWM duty cycle. So if I were to make a really nice structure, I would keep the PWM in the HAL, and then I would make a driver layer, and I will have the servo logic in the driver layer of the software. So the point being that the HAL is like a very thin layer over the hardware, and in this case, the purpose of the HAL is to simply configure the PWM peripheral in this chip. While the this servo is not directly a part of our platform hardware. So I feel like this would fit more in a driver layer. And then on top of the driver layer, we would have the application code, which would work with the servo driver, which would work with the PWM here, finally controlling the servo the way we want. Let's see what AI did here. Yeah, that looks okay. Make a test function for the HAL control. This time it should use timed movements. At first, it should position in the center, then move to highest value for 1 second, then to the lowest for 1 second. It should ask the user if the servo moved accordingly and to type P for pass or F for fail. That would be the wrapping up of our little servo chapter. If AI can do this for us, then I feel like we have handled the management of the servo very nicely. Yeah, I didn't actually specify the if the PWM should be kept running. This is not industrial strength. I mean, you would need to have. I would say you would need to be able to cut the power, perhaps. Or whatever is necessary in a proper application. But definitely you would need to be more careful about the lifetime of our signals. Do we need the pulse width train, the train of pulses to be generated at all times, or only when we need the servo to be active, and so on. Let's just keep it. Let's move the test function here. To be the first test, and let's see if it works. Okay, we didn't really see the beginning of that. Let's just reset the code. Middle, left, right. Did the servo move center, high, low? Okay. We passed the test. Let's wrap up the video here, and I will say that this went way beyond expectations. We didn't have to redo anything that the AI did this time. I think the rules and skills made things better, and we have a very good platform now for developing hardware. Thank you for watching, and see you in a future video.